A periodic signal does not begin at 0 seconds. It has a past and a future, and both are practically symmetrical to the present. However, the spectrum up to now always begins at 0 Hz. The equivalent to the past would be negative frequencies in the frequency domain. Negative frequencies seem not to make any sense, because it does, at this moment, not appear possible to interpret them physically. But we should take nature's symmetry principle seriously enough to look for effects where negative frequencies might provide the key to understanding. An extremely complex signal produces a spectrum which consists of two separate, equally steep-edged and broad frequency bands. By skillful manipulation of the signal, the two frequency bands are moved step by step to the left in the direction of 0 Hz, without changing their bandwidth or the distance between them. What happens when the lower frequency band rises above 0 Hz? It can be seen that the negative spectrum appears in the positive area as if reflected and overlaps the positive area. If the frequency is further displaced, the positive frequency band moves further to the left. The negative frequency band, on the other hand, moves further to the right. The formerly lower frequencies are now the higher ones, and vice versa. This observed process is understandable if we allow negative frequencies. We open the FFT menu and choose Fourier analysis, and then Symmetrical Axis. Now look what happens. As you will see, the spectrum is always symmetric. That means the frequency domain stretches, like the time domain, from negative infinity to positive infinity. If the spectra move towards 0, they will overlap after crossing the 0 line. At the top, we see once again the 3D spectrum of a narrow periodic rectangular pulse. Look carefully at the playing field of the sinusoidal signals, particularly where the rectangular pulse is symmetrical to 0.5 seconds. As the pulse duty factor, tau divided by t, is roughly 1/10, the first 0 point of the spectrum lies at the 10th harmonic. The amplitudes of the first 10 harmonics at 0.5 seconds on the playing field point upwards. Those from 11 to 19 point downwards, then upwards again, and so on. It would therefore be better to enter the amplitudes of the amplitude spectrum in the second, in the fourth, in the sixth, etc. sector, 11 to 19, pointing downwards instead of upwards. At the bottom, you see the continuous amplitude spectrum of a one-off rectangular pulse. If the curve is drawn downwards in the second, fourth, sixth, etc. sector, it ought to begin to dawn on you that what you see is the right-hand symmetrical half of the SI function. And last but not least, if we describe the SI function symmetrically towards the left, in the negative frequency range, we obtain the total SI function, to be exact however, only half as high as the upper spectrum, because half the energy is allocated to the negative frequencies. A characteristic of symmetrical spectra is a regular and inverse part of the spectrum. Here you see a symmetrical spectrum of a low pass. Every low pass is also a band pass with a medium frequency of 0 Hz. Both halves of the spectrum are symmetrically identical. They contain above all the same information. However, the low pass cannot start at 0 Hz because it would then have an infinitely steep sloped filter edge. This would not be in accordance with the uncertainty principle. A bandpass also has a symmetrical counterpart. Please note that the expressions upper and lower cutoff frequency ought to be used with care in connection with the regular and inverse positions. Here you see the symmetrical spectrum with regular and inverse position of an audio signal. Some computer programs always present the symmetrical spectrum in the frequency range. The symmetrical spectrum is also automatically provided by the FFT mathematics. In this case, however, half the screen would be used up for redundant information. The diagrams once again summarize the symmetry features for two complementary signals, a sine and delta pulse and an SI function and rectangular function. From now, every sinusoidal signal has two symmetrical sized frequency, plus f and minus f. But we should still prove that two lines in the time domain have a sinusoidal-shaped spectrum. The important insight is, signals in the time domain may occur in the same form in the frequency domain, and vice versa, if negative frequencies and amplitudes are admitted. The time and frequency domains represent two worlds in which similar figures projected into the other world produce identical copies. Does a sinusoidal amplitude spectrum really exist for reasons of symmetry? An interesting question which may be regarded as a test case for the symmetry principle. One line in the time domain results in a constant progression of the amplitude spectrum, just as a single line in the amplitude spectrum results in a DC voltage in the time domain. Two lines produce a cosine-shaped or sinusoidal progression of the amplitude spectrum, assuming that negative amplitudes are admitted, just as two lines in the amplitude spectrum guarantee a cosine-shaped or sinusoidal progression in the time domain. The phase step from pi, or more precisely from pi half to minus pi half, to the zero positions of the sinusoidal amplitude spectrum is proof that every second half wave ought to lie in the negative range. With regard to the Fourier transformation, the time and frequency domains are largely symmetrical if, as already mentioned, negative frequencies and amplitudes for the spectral area are admitted. The phase spectrum provides the explanation for the sinusoidal course. You may have had the following idea. If one delta pulse results in a constant spectral course, since all frequencies have the same strength, two delta pulses should theoretically result in a constant spectral course, which is twice as high. This idea is not entirely wrong, but it applies only to those points where the sinusoidal pulses with the same frequencies of both delta pulses are in phase. This only applies to the 0 points of the phase spectrum. At the shift points of the phase spectrum, the sinusoidal pulses with the same frequencies of both delta pulses are dephased exactly by pi, and thus eliminate each other by interference. Between these two extreme points, they amplify or decrement each other, depending on their relative positions in the phase. Remember, periodic signals have line spectra. The lines are equidistant and are integer multiples of a basic frequency. As a result of the symmetry principle, the following should hold. Equidistant lines in the time domain ought to produce periodic spectra in the frequency domain. This is now investigated experimentally. In the first series, you see the line spectrum of a periodic sawtooth function. In the second and third series, you see periodic delta sequences of different frequencies, both in the time and frequency domains. This is a special case in which both occur simultaneously in the time and frequency domains, periodicity and lines. The fourth series shows a one-off continuous SI function, which has a relatively narrow continuous spectrum. If this signal is digitalized, that means presented as a chain of numbers from a mathematical point of view, this is equivalent to the multiplication of this continuous function by a periodic delta pulse sequence. In this case, by the delta pulse sequence of the third series. This is shown in the bottom series. As a result, every digitalized signal consists of a periodic but weighted delta pulse sequence. Therefore, every digitalized signal also consists of equidistant lines in the time domain and must therefore have a periodic spectrum. Most important for digital signal processing is the following consequence of the symmetry principle. Equidistant lines in the time domain create periodic spectra, as periodic signals in the time domain cause equidistant lines in the frequency domain. Fourier transformation is symmetrical. A periodic sawtooth signal with 4 Hz is selected as a test signal. You could, however, just as well take any other signal, for example noise. At first, A complex FFT with two outputs transforms the signal into the frequency domain. Then an inverse FFT retransforms the signal back into the time domain. Input and output signals are identical, which proves the symmetry of the Fourier principle. Now we show an important application. If we cut out frequencies in the frequency domain, we get filters of highest quality. Here in the module cutout, the frequencies from 0 to 32 Hz are allowed to pass. In the case of the settings selected, the sample number is practically equivalent to the frequency. You see the highest frequency of 32 Hz as a ripple content of the sawtooth. This ripple sign contains 8 periods on any sawtooth flank. In the case of a 4 Hz sawtooth frequency, the highest frequency allowed to pass is 4 times 8, which means 32 Hz. It is very important to set exactly the same cutout on both channels. Frequency domain. For the transformation from the time to the frequency domain, we require the module with one input and two outputs. The reason is that we need 2 bits of information about every frequency: amplitude and phase. We continue to explore and add an XY module. Now you see a number of frequency vectors on the screen. Each of these frequency vectors has a symmetrical twin in relation to the horizontal axis. At the top, you see the sinusoidal signal with varying phase shift. In the XY plane, we see the instantaneous phase angle of the twin vectors relative to the vertical axis. We call the vertical line sine axis because both frequency lines with a phase displacement of 0 degrees cover the vertical axis. We call the horizontal line the cosine axis because the frequency lines of the sinusoidal signal with a phase displacement of 90 degrees cover the horizontal axis. We show in this illustration that the sinusoidal signal, which belongs to the frequency vector pair, can be produced from the addition of the sinusoidal signals which belong to the real part and the imaginary part. The 2 frequency lines apparently possess the characteristics of vectors which, in addition to their absolute value, also have a certain direction. We see that the length of both frequency vectors reflects the amplitude of the sine, whereas the angle of the frequency vectors in relation to the vertical and horizontal lines reflects the phase displacement of the sine and cosine at the point of time 0 seconds. The 2 equally large cosine parts of a frequency vector pair add up to a quantity which is equal to the momentary value of this sinusoidal signal at the point of time 0 seconds. By contrast, the sine parts always add up to 0 because they are opposite to each other. Because there are quantities along the cosine axis which are measurable in a real sense, we call this the real part. As on the sine axis, the 2 components cancel each other, we choose the expression imaginary part according to the mathematics of complex calculations. This illustration shows the direction of rotation of the two frequency vectors. The negative frequency at the bottom rotates in anti-clockwise direction. The positive frequency in a clockwise direction. For the sinusoidal signal with the phase displacement of 30 degrees, we obtain the value 2 by projecting the vectors onto the cosine axis. The sum is 4. The projection onto the sine axis results in the value 3.46 or minus 3.46, which means that the sum adds up to 0. For this reason, the resulting vectors of all symmetrical frequency vector pairs are always situated on the cosine axis and represent the real instantaneous values at the point of time 0, which can be measured. For this reason, the so-called real part is represented on the cosine axis. This is a spectral representation of a periodic sawtooth in the Gaussian numerical plane. Periodic signals contain only their common multiples of their basic frequency in their spectra. In contrast to the previous case, we expect many frequency vector pairs. You can see a periodic sawtooth oscillation with a varying phase displacement. You can also see how rapidly the amplitudes decline with increasing frequency. The lower the amplitude, the higher the frequency. Here you can see a low-pass filtered noise with a cutoff frequency of 50 Hz. That means a non-periodic signal. This type of signal does not produce any law with regard to amplitude and phase, as it is of a purely random nature. You can clearly see the symmetry of the frequency vector pairs. The two corresponding higher and lower frequencies are directly connected to each other. That means one line leads to the lower frequency, the other one to the higher frequency. This model makes it very difficult to find the beginning and the end of the general line. Here we see the frequency vectors of a one-off delta pulse. The frequency vector pairs in this illustration are all on one circle, because all the frequencies of a delta pulse have the same amplitude. However, the phase varies considerably from frequency to frequency, so that the neighboring frequency vector pairs are arranged in a circle-shaped symmetry. From the theoretical point of view, the frequency vectors rotate infinitely in a circle. In this example, the phase shift of the first 24 frequencies form the first rotation of an endless sequence of circles.